Okay, welcome back. This is P Dog with his with Chapter 6 lecture for 6.1. Okay, and we are this is for organizing elements and the organization of the periodic table. So, our first objective, students will describe the ideas behind the development of the periodic table. And this is the first question over here that I want you guys to practice with your materials. How did chemists begin the process of organizing elements? Well, chemists have been sorting the elements according to natural groupings based on their properties, and most of the elements have only been discovered in the last 200 years. So they didn't really have a whole lot to go on when they were trying to organize their elements. There were early periodic tables. First of all, it used to be just a list of elements because there were only 30 known by the end of the 1700s. And then Dalton comes along with his atomic theory. Dalton's atomic theory comes along, and all of a sudden people know to look for elements by looking for atomic masses and looking for individual atoms. So, by the early 1800s, a German chemist by the name of J.W. Dobereiner classified the elements into triads, or sets of three, based on their similar properties. And the elements also agreed with the differences in the atomic mass. So, for example, if he knew that calcium had a mass of 40 and barium had a mass of 137, he could add those two together, divide by 2, and find the mass of the element that was in between them at 88.5. And this was remarkably accurate considering the mass of strontium is 87.6. It was just a neutron off of the actual atomic mass. Okay, not only does strontium have an atomic mass, it's right in between barium and calcium. It also has physical properties that are physical and chemical properties that are also right in between them. It's a little bit less metallic than, more metallic than calcium, and a little bit less metallic than barium, and has other properties like that. Okay, then in 1865, J.A.R. Newlands came up with the law of octaves, and essentially, but by this time, within the last 60 years, they discovered 62. They had known of 62 elements. That's another 32 elements in the last 65 years. And they were finding elements very quickly, like one every 2 years at this point, because they knew what to look for. Newlands arranged the elements by their atomic mass, and every eighth element had the properties of the first. And the second had the properties of the ninth, and the third had the properties of the 10th. And this is very similar to a musical octave, which is why he called it the law of octaves. There's an interesting vignette that we can go over right here in regards to this era in history and how scientists and natural philosophers were trying to find a natural beauty in things. But that would be a discussion for another time, and come on in and see me at lunch if you want to talk about that, or you can email me. Newlands did recognize that there was a periodic pattern or repetition to the property of elements. I do want to point out a mistake that I have here in my notes. This right here should not be helium. That should not be there. Hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and so on are what should be there. And we knew we did not have helium because the noble gases were not discovered yet. But there was this periodic pattern that hydrogen was kind of by itself, and then lithium would be similar to sodium, and beryllium was similar to magnesium, and so on. Okay, this idea was expanded by Mendeleev, a Russian chemist who worked independently of Newlands, but arranged elements in very much the same way. He organized by increasing atomic mass and a repetition of properties. Now, if you remember the Hunting the Elements video in my class, you remember seeing his periodic table mounted on the wall of a Russian building. Well, here he is. This is the man. Okay, Mendeleev. He's on a postage stamp, which is, of course, the proper way to commemorate anybody who makes a significant achievement to the history of science. You put him on a postage stamp. And here is his periodic table. Now, you'll notice that there may be question marks. For example, here and here, and here. And he was able to predict with high precision not only that there would be elements here, but also what their masses would be. This one turns out to be scandium. This one is, I believe, is gallium. And this one is germanium, named after Scandinavia, Germany, and France. Yes, gallium is named after France because the ancient name for France is Gaul, and that is what Caesar conquered way back when, and it is now, they now have the name France. And that takes us to our next page. Okay, Mendeleev predicted the missing elements of scandium, gallium, and germanium, and that other gaps would eventually be filled, and there were only 63 elements known at that time. W. Ramsay comes along in 1890 and discovers the noble gases, and he adds the last column to the table. By the way, you should be able to answer this question by now. What property did Mendeleev use to organize his periodic table? And this brings us to the modern periodic table, because at this point we had finally discovered the number of protons. The periodic means recurring patterns, so the periodic law is when elements are arranged in order of increasing atomic number. Their physical and chemical properties show a periodic pattern. Our current periodic table organization was developed by Henry Moseley in 1910, once we knew about the proton and we started understanding the quantum arrangement of electrons. And so he arranged the elements by their atomic number, including the noble gases based on X-ray emission frequencies. And these are just like the bright line spectra, except they are in the X-ray range, and these can determine the amount of protons an atom has. Now mind you, Mendeleev was partially correct. He recognized that the periodic pattern was there, but he based his periodic table on a less accurate property of atomic mass than the exacting properties of the atomic number, because you're counting exact protons. Now mind you, don't confuse the properties, don't confuse that the properties of the elements are still determined by electron configuration, but the number of electrons is determined by the protons. So now, some general classes in the periodic table. We have the zigzag line that goes down there. This separates the metals from the nonmetals. The elements on the line are called semimetals or metalloids, and the exception is that aluminum and polonium are both metals. Okay, and then we have the properties of metals. Metals are malleable, which means they can be pounded into sheets, like Rutherford's gold foil. They are ductile. They are ductile. Okay, which means they can be drawn into wire. Okay. They have luster, which means they are shiny. They are good conductors of heat and electricity, but you know this, that you know to not touch the oven rack once you've heated up the oven, because it'll hurt. You know to not put a fork into the light socket because it will hurt. These are both because they are good conductors of heat and electricity. And they have relatively, and here's another goof that I have, unfortunately. This is not low. This should be high melting points and boiling points. They have high melting points and boiling points, and most of them are solids at room temperature. Okay, that brings us to the properties of nonmetals. They are generally the opposite properties of metals. Okay, they are brittle. Okay, so they're not malleable or ductile. If you hit them with a hammer, they will shatter rather than flatten. They are dull, okay, and not shiny, or they're just invisible, like a gas. They are poor conductors of heat and electricity, which is why we use them for insulation. And they have relatively low melting points and boiling points. And most of them are even gases at room temperature. Okay, the third broad class is a semi-metal, and it's the ones along the zigzag line. And these are intermediate properties between metals and nonmetals. So for example, metals conduct, nonmetals don't. So semi-metals are semiconductors of electricity. And so computer chips are made out of silicon, which is a semiconductor. doped with elements gallium and arsenic, which can either reduce or increase their electrical conductivity. Okay, that is it for lecture 6.1, and we'll see you next time for lecture 6.2. So this is B-Dog signing off.